and I'm delighted to do so. Maria is a student is my student up in Edinburgh, where she's doing her PhD on probabilistic programming. But please, folks, I see Gabriel, Paul, Ian, please put your videos on so we can actually see each other. Fantastic. That'll just make it a little bit more intimate, because I'm sure, if possible, Maria would like to make this interactive. Ron, Cyrene. Great to see Alexandra, lovely to see you. I think with these remote sessions, it's quite important to try and include people from the start, or else it feels a little bit remote. So it's great if folks can put their cameras on. Serena, thank you so much. Alex, great to see you.
Hi, remember there's more people watching you on the YouTube stream, so it's not just 11 people watching.
Well, we can't. Great point. Great point. Welcome to everyone on YouTube as well. Oh, there's Ron. Good on you. Oh, and someone's in chat. And there's Tony. Great to see you. I have no camera on this computer, unfortunately. Oh, that's too bad. Thanks anyway, Ian. So I think we should kick off, but if there's a raise hand functionality in Teams, so I think if you'd like to ask a question of Maria, you know, do raise your hand, and we can, let's see how things go. So we actually have like 40 minutes plus 40. So I think if we, I think there is time to take questions during your presentation, Maria. But if it gets out of hand, if we're overwhelmed, maybe we should just let you get going. But I'd say for now, let's just kick off. So delighted to have you presenting, Maria. Over to you.
Thanks very much. I'm delighted to be here as well. Very excited for this. And yeah, today I'm going to talk about probabilistic programming, and more specifically what probabilistic programming is, why it's a useful tool, and how we can make it better. So I have some slides. Let me just figure out how to share my screen. Okay. Can you see my screen?
Yep, that looks great.
Perfect. All right. Okay. To do it. Ah, this is still not working. Sorry.
No worries. Just take your time.
Okay, I'll try again. Let's see, what about now? That good?
Yeah,
perfect.
We can see your slide.
Yes, perfect. All right, so I would like to start with just a simple brain teaser that kind of introduces probabilistic programming, and that's the problem of Monty Hall, which I suppose many of you had heard before. I know you can. I see some notes. Okay, so I'm gonna go quickly through it then. The Monty Hall problem, basically, it goes like this: you're taking part of a TV show, and there are 3 doors, and behind one of the doors there is a lovely sports car, and that's like the prize that you're aiming to win, and you really want to win this. And then behind the other 2 doors there is a goat, and you will choose a door. There's some rules to the game, and at the end, like, you end up with a door that you open, and if you win whatever is behind the door. So you're aiming for the sports car here. All right, so it goes like this: you make an initial choice, And then let's say you choose door number 1, but you don't open it. And then Monty Hall, the host of the show, will go ahead and open one of the other doors that you didn't choose. But here is the deal. He is always going to open a door that has a goat behind it. He's never going to open the one with the car. And now the question is, should you stay with your initial choice, door number 1, or should you switch to the other unopened door? Or does it like not matter? What's the answer? And perhaps a little bit counterintuitively, because it feels like nothing changed here, right? There is no reason for this not to be 50-50, at least intuitively. But it turns out that actually, if we work out the probabilities, there is 2/3 chance of winning the sports car if we switch to door number 3. And like, look what's going on here. That's really weird. How is that happening? Intuitively, we started from 1/3 chance of the car being behind each of the doors, and that's like we were with door number 1, right? And then Monty opened one of the other doors, but there is no reason why him opening a door will increase your probability of your already chosen door. That doesn't make sense. But the final probability of the entire system needs to sum to 1. So the probability of your door will stay at 1/3, and then the other 1/3 from door number 2 is kind of like gonna go to door number 3. So this is like kind of the intuition. Right. And if you don't believe me, we can actually, you can go and like write a simple, I don't know, Python script or whatever your choice of languages, and you can just like simulate this and like generate many scenarios. So here you see like each of those is a scenario where we picked door number 1, and then Monty chooses either door number 2 or door number 3 based on which one is gold and stuff like that. And if we do this many times, and then we reject, just like, you know, scrap all the scenarios that don't match our data, which is that Monty opened door number 2, we're going to see that we're going to be left with approximately 1/3 of the scenarios being the car being behind door number 1, and the other 2/3 behind door number 3. And okay, so you probably noticed I mentioned there's something which was like, you can go ahead and code this. You can just write the simulation. And here's like, we're kind of slowly getting into probabilistic programming. So here is a kind of pseudocode program that would generate generate scenarios for Monty Hall, right? So we have doors 1, 2, 3. Then we're gonna set the car to be one of 1, 2, or 3 at random, right? And then we're gonna pick at random one of the 3 doors, and then Monty is going to pick at random one of the doors that are left when we remove your pick, and the door that has a car behind it. And this generates scenarios. But now that's not quite a probabilistic program yet. What makes this program probabilistic is that we observe some data. So we're gonna observe that in this case, pick is 1, because we picked door number 1, and Monty opened door number 2. And so this is kind of like the gist of probabilistic programming. We have some usually generative process that describes how we generated our data. Then we observe some data over here, and then we work backwards to figure out how the beliefs about our system, our beliefs about our system change based on our observation. And this process of working backwards to figure out the beliefs over parameters of our system is called inference. All right, so here we have a very simple program. We can for this particular problem, we can work out the posterior analytically. You can sit down and derive the probabilities by hand. You can also do what I showed earlier with the simulation, where you just reject things that don't match your data. This is called rejection sampling. But the idea of probabilistic programming is that we can have more complicated programs. So we can have, in this case, we have a program with several continuous variables. And if we do the same here, if we do, say, rejection sampling, we're going to accept a sample. So we're going to not reject with 0 probability every time. So this is infeasible. And in many cases, we also can't derive this posterior probability analytically. So for this reason, there have been a lot of algorithms designed that can do approximate inference sort of automatically, given, say, some sort of specific joint distribution or something like that. But in general, for a general program, inference is very difficult. So this is like kind of the important thing behind probabilistic programming, that the backend is really, really hard to implement for general class of models. Okay. Before we continue, I'd like to just make sort of give a little bit of metaphor that compares probabilistic programming to conventional programming and to deep learning, because you're probably thinking, oh, okay, so we have some data, we input some data, we're trying to approximate some parameters. That sounds like deep learning, but it's not quite the same. So in conventional programming, we input some, say we have a function in conventional programming. It takes an input x, it gives an output y, and we've also specified the function f. And the task is to just compute the output y, right? In deep learning, we typically have inputs x and outputs y that are our examples, say these images of a cat, these images of a dog, and so on. And what we are trying to do is to approximate a function that maps x's to y's. But with probabilistic programming, it's a bit different. With probabilistic programming, typically, we can think about it as having the output, the generated output y, and wanting to somehow approximate the probability distribution over the input x by also having some random. So we are also provided some random function f, so function with random variables in it. So it's kind of like inverse programming. You can think about it that way. Okay, so what is this suitable for? Why would we use one or the other? Probabilistic programming is very useful when we want to quantify uncertainty. So remember how I said, like, we want to compute a probability distribution over this input x that generated our data. So we are interested in a probability, in an actual quantifying uncertainty properly. It's not data hungry, it's not like deep learning, so we can use it with very small amounts of data. It's actually a way to make sense of small amounts of data. We can incorporate knowledge from different domains that we don't, in deep learning, for example, we might not be able to, because everything is so black box there. And for probabilistic programming languages in particular, the main goal is to separate modeling, which is writing this generative model, from the actual task of inference, so that users can come from any field and they can only write something that generates the data and then learn from it. And there are lots of success stories. So here, for example, we have a picture, which is a probabilistic programming language for scene perception. And here we'll have a model that generates 3D faces, 3D scenes in this particular task phases. And then we'll generate also position of the face and intensity of light and stuff like that. And then it's going to take a snapshot. And the task is you actually input an image of the snapshots of the face, and you want to reconstruct the model, the 3D model of the face. Another very interesting example is more recent, and it's about particle physics, and it's very, very exciting. So we can, in particle accelerators like the Large Hadron Collider, we have, so firstly, we have a lot of machinery that is noisy, so we are not sure what we've observed and stuff like that. And secondly, the interactions between particles themselves, there are also probabilistic. So when two particles interact, so one of several things can happen. So we can describe all of this, so we can describe something like the standard model with a probabilistic program. And then we can run the Large Hadron Collider, get actual data from what the detectors detected from collisions, and figure something out about the standard model, such as, is it plausible that the standard model is correct? Another favorite of mine is astrophysics. So here, in a very similar way, we want to learn about the parameters that generated our universe that we don't know about. But the only thing that we see in the universe is actually a projection on the sky of all the stars that the light of which can reach us. So we can actually write a model that we believe might be true about the universe, and observe this data that we see. So the model will generate the universe and project on Earth, on the sky of Earth, what should be seen. And then we input the actual things we see and work out backwards things about the universe. This year, there has actually been a lot of success stories of probabilistic programming, because it turns out that one case in which it's very important to quantify uncertainty is when we are dealing with healthcare, where we are dealing with viruses spreading all around the world and all that. So this is like a very incomplete and out of date list of some papers just from this year that work on COVID and do so with probabilistic programming. Okay, great. All this is awesome, but there is a little catch. Why is it the case that, I mean, yes, there are some success stories and all of that, but why is it the case that probabilistic programming is not used more widely? It turns out that because of what I said earlier about inference, so because inference is very difficult, we often need to do all sorts of sacrifices when we design a language so that we feed it with a particular inference algorithm, say. And here is, again, very outdated sort of snapshot of probabilistic programming languages from it ends a couple of years ago. So not everything is there. There's so many, but you can see that there are like two big groups that say discrete random variables only and bounded recursion. So these are only two of the possible restrictions we can put on our probabilistic programming language in order to make inference work. These are things we do that, yeah, for every language it will be different, and there are so many. So here's a longer list. We have things such as, in many cases, we only can have bounded recursion, which is when we can't have random number of random variables. Very often we can only have discrete variables, which is not very useful for a lot of real world tasks. In other cases, we can only have continuous variables, things like requiring tractable likelihood or differentiable likelihood, and so on. So there are a lot of these requirements. And if the dream of probabilistic programming is to find a language that is fast, user-friendly, and general, where user-friendly kind of includes being automatic, so we don't have to write inference ourselves, we actually live in the sad reality of pick 2 out of 3. So we'll have to sacrifice on at least one of these to make things efficient. And that leads me to my research that I do at Edinburgh, and Andy's supervising, which is about applying programming languages techniques to existing probabilistic programming languages and systems in order to kind of improve them on one of those 3 axes that I showed without sacrificing anything. So either make them compile them so inference is faster, or make them more usable, and so on. And the language I work with is called Stan. Is one of the, perhaps the most widely used probabilistic programming language. It has thousands of users and is used in the sciences, in engineering, in businesses. Some of the examples that I showed earlier, so a lot of the COVID examples, the astrophysics example, were all with Stan. And Stan is one of the reasons why it's so successful is exactly because it restricts the models you can write in it so that it can compile to fast inference algorithm that is called Hamiltonian Monte Carlo. So it's very fast. Just a side note here, the examples I'm about to show in this presentation are actually not in Stan, but in Slickstand, which is a project we did a couple of years ago, which is sort of like a blockless, more composable version of Stan, but otherwise very close to it. All right, so for the rest of the time we have, I'm going to work through one of the sort of programming languages techniques that we applied for a particular problem that can be made better with Stan, or more automatic in this case. All right, so let's see this model. So this is written in Stan or Slickstand, and you can see that the syntax is very similar to the pseudocode we had before. We just have some types and the data. So the observation is actually specified with this keyword data. What this model does is a change point model where we're trying to figure out when a change point occurred for some for the rate of happenings of some event. So say that we are counting numbers of disasters per year. So we input this array Y is really a number of disasters for T different years. And we say that there is a change point, D, before which the rate of disasters is E, and after which is L. And we say that so the number of disasters each year is distributed according to a Poisson distribution with either E or L, depending on are we before or after T. But here's the thing, I kind of lied. This wouldn't work in Stan. You can't write this in Stan. And the reason you can't is because one of the side effects of using Hamilton and Monte Carlo is that it requires the gradient of the joint probability defined by the model. So we want to, in order to make inference faster, we're going to do a physical simulation inside of the inference algorithm, for which we need the gradient of this. So the data in theta is the parameters of the model that we are trying to find. And this immediately means that theta can't be discrete, because if theta is discrete, this joint function is not going to be, is going to be almost everywhere not differentiable. Or everywhere not different. It has to be piecewise continuous, and it's not. So that means we can't have discrete parameters, and you can probably see where I'm going. In this project, we took Slickstand with discrete parameters, so like this change point model that I showed before, and we automatically translated to regular stand so that we can still use Hamiltonian Monte Carlo. And how does that work? Well, there's a trick that I'm going to show now. Here's the change point model again. So one way of thinking about it is, as we've already discussed several times, as a generative model where we just, or where this sim operator here says randomly draw from a distribution. But really what this model encodes in Stan is some joint probability distribution, or density, joint probability density. And this is joint density on the data Y, the continuous parameters E and L, and the discrete parameter D. You can write it, it factorizes like that, which is defined by the model. And the idea is that this joint density is actually proportionate to the posterior, which is the distribution over E, L, and D given Y. And this can be used for inference, but I'm not going to go into details how. So one thing we can do is we can actually still work with this program by summing out the discrete variables D. So if we just, so we can just derive the joint density over the data and the continuous parameters only by marginalizing out D with a sum. And this is how it looks as a program. We're going to have some array with of size T, and when each element of the array is going to be it's going to correspond to a different year of change, a point of change that we're considering, right? So like ACC1 is going to mean that we are now considering that the change point happened during year 1, and so on. And then we're going to compute for each of each possible value that D can take from 1 to T. We're going to compute the probability, the joint distribution of the model. And at the end, we're going to sum this. And you can probably see that, for example, here, these two things don't depend on D at all, and like here as well in this sum. So we can actually take those out. So yeah, we take them out like this here and like this here. And this is what our project is about. So it's about taking a program that looks like this and transforming it to something efficient that makes sure that nothing that doesn't have to be inside of a for loop isn't in a for loop. And then the interesting thing is that we can actually also generate again the discrete parameters given the continuous parameters we sampled in this stage. Oops. Okay. So the key idea is how we do this. Well, the key idea is that we're going to use information flow analysis and type inference to find certain conditional independence relationships between variables in the program. And based on these conditional independence relationships, we can actually slice the program in the right way so that it's as efficient as possible. Here is a bigger example where we see how we take, so in this case we have marginalized out only one of the variables, And the way we do this is that we kind of like detect the statements that correspond to that variable, and they may or may not contain it because of the way information flows. And we're going to eliminate that here and then pass some information along the neighbors of this variable in the original program. And I think I talked too fast because that brings me to the end of the talk. So this talk was about probabilistic programming, what probabilistic programming is, why is it hard, and how can, like, one possible way that we can think about making it better, which is applying programming languages techniques to rewrite probabilistic programs in a way that is going to make inference more efficient or is going to allow for more generality. And I think this means we have more time for discussion.
Fantastic. Let's thank Maria for her presentation.
Thank you.
We have time for questions.